All right, welcome everybody. For those of you who have not attended Santa Barbara JavaScript Meetup before, we are Santa Barbara JavaScript Meetup. Now we're a group of local enthusiasts. We meet once a month to talk about all things JavaScript. A couple of little housekeeping announcements before we get started. I want to thank our sponsors, first and foremost, WorkZone, for hosting us tonight. Thank you, WorkZone. WorkZones is a co-working and shared meeting space. If you're interested in checking out what they have to offer, see Paul afterwards, and he can hook you up with a guest pass to try it out. We also have PayJunction as a sponsor. They host us a few times a year and provide pizza and drinks and things like that. We have Invoca, co-organizer Garvin is employed there. All right, capture the flag this weekend, guys. Right on. And then lastly, we have a partner relationship with O'Reilly Media. We get discounts on books and videos and conference passes. And if we use the conference pass discount 3 times, I get a free conference pass. Next month, we have Sean Emmer talking about production grade Redux, location TBD, working on that. April, we have my coworker, Marcus Benalis, with a TBD topic at a TBD location. After that, we're wide open. You want to speak, stand up here where Tyler's going to stand tonight and dazzle us with your JavaScript knowledge. Let me know or let Garvin know. We definitely want to get you on the calendar. You don't have to be an expert. No topic is out of bounds as long as it at least tangentially touches JavaScript. Beyond that, I don't have anything else, so I'm going to turn it over to our tonight's speaker, Tyler Alves.
Oh, I pressed the button. All right, I think we're good. Yep. All right, I'm Tyler. I'm going to be talking about how you can bridge the gap between the interview and your day job. And why did I pick this topic? Well, I've been hiring engineers at Uber for the last few months. And I always ask people for feedback in the interview process. And our interview process includes some pretty easy level algorithmic questions. But time and again, I get the complaint that algorithm interviews aren't relevant to day job. People, even experienced people, come back with this complaint that they're like, why should I have to do this? I never do it on the day job. And so really, and I felt this way from time to time too. Like when people have said that, it's really struck a chord. When I've been interviewing, and I've been interviewing recently as well. So I've also felt this way, and it's kind of also to prove to myself that this stuff is worth learning, not just for passing an interview, but also as a skill that'll really help you in a day-to-day job as a developer. Yeah, so taking the time to think through realistic scenarios not only informs me on what I should ask the people in the interviews, like we have to ask them algorithmic questions. It's really the only way for me to see how someone thinks through a tough problem. But I can choose what type of algorithmic questions. So if I can think of a realistic scenario that this algorithm applies to, I'd much rather ask that than to straight up ask someone like, balance a binary tree or something like that. And no, we're not going to talk about that. And no, I probably couldn't do that for you. Finally, I just want to point out that I'm not the biggest expert here. Again, I made this presentation as a way to kind of get myself to study these things, to get myself psyched. So any questions I'd be happy to answer. But I would also be happy if someone who knows more than myself didn't just ask questions, but provided some context of their own to the presentation. So let's move forward with this as a discussion and not just a talk that I'm giving. So before we really jump into too many more complex algorithms, first of all, let me say this talk, we're going to try to keep it to like 30 or 40 minutes. So obviously, we're not going to go through the entire range of computer science here. But before we start, we're going to start with some building blocks. And I know for a lot of people here, these are just kind of going to be like obvious to you. But I would encourage you to kind of sit through, stay engaged. I think what can commonly happen with experienced engineers is they're like, I know what that is. And then if you really ask them to elaborate, maybe the fact that you know what it is stopped you from keeping yourself fresh on it and take another look. So I'd ask you to just stay with it and see what you might freshen up on. So starting out with call stack, it's a list data structure that keeps track of the active functions as well as the lines where each should relinquish control when they return. So that definition may be great for you. For me, it gave me kind of an idea, but this example should kind of help you out there. If we look over on the right-hand side, we have the call stack, and we have some code, and we're just going to walk through the code and kind of see how the call stack stacks up. Here we go. So when this code first begins to execute, it's going to create something called an execution context. And what that is kind of like it's going to do this for the main function or the global function, if you will. And it's going to create all the local variables that that function needs, and it'll add it to the call stack. So here we go. And so this code's going to execute. It's going to get down to line 10, and it'll main will be in the call stack. Each of these blocks again are just called an execution context. And then when it gets to 10, it's going to do something interesting. It's going to call sum3 with the number 7. And it's basically just going to wait for sum3 to return something, right? Now, you see we have the line number here as well. So when sum3 returns, it'll return to that line number within main. So we're going to call sum3. It'll be added. Its execution context will be created. This variable 3 will be created. It'll be added to the call stack on top. And then, so it's at line 6. Now it's just going to move to line 7. And then you can see here, again, it's going to call another function. So now an execution context is going to be created for sum, and it'll be added to the stack. So now we'll see that sum just returns. And when it does that, the sum function, as well as the two local variables a and b, are no longer needed anymore, right? When you return from a function, you don't need the function anymore. There's nothing, it can't do anything else. You've already returned. And likewise, you don't need its local variables, because if you're not doing anything on them, then you don't need them. So we'll go ahead and pop that off the call stack when it returns, and we'll clean up those local variables a and b. So now, as you can see, it popped off. Sum3 became the new top item on the call stack. So we return to line 7, sum3. Again, it's going to return. So it'll be popped off. We'll return to main, and we'll print 10. So the call stack may seem to you like some arbitrary information, like why do I really care? But it turns out, as we'll see in later slides, that it can tell you a ton about what's going on in your program. I think probably most of you have seen like an error that showed you the call stack, and maybe you've seen that it's been helpful, you know, like, oh, my error may have occurred in this function, but really it's 3 functions down that pass the wrong data type or what have you. But we'll see that they're also great for analyzing some of these algorithms and understanding how other concepts work. Yep.
Is the console log considered part of
so the call to console.log is considered part of main, but you have to remember that console.log itself is also a function, right? So if we were to, we can actually look at that exact example later, but if we were to like really look at it, you can step into the console.log function execution context, if you will. How can we put all of these into one answer? Okay, lexical scoping. So lexical scoping is another building block I kind of have to go over. This one I'll go over a little bit more quickly. It's just the protocol used in a JavaScript parser to resolve variables. And if we kind of break that down a little bit, some of the rules of scoping, it defines the rules that are used when variables are used. So nested functions have access to variables declared by their parents, and then variables at level take precedence. So if you declare a variable team, for instance, like the Broncos, and you had a function inside of that function that, again, defined team as the 49ers, then within that function, it would choose the net. It would choose the lowest level. So it would choose the 49ers. I think that's probably clear to most people that have observed that in your code. So let's move on to closures. Now, closures are one that I think is pretty common in the JavaScript interview. And I think it's one that even some experienced developers will kind of get stalled on an interview and not really be able to explain. And unfortunately, they'll go home and kind of do like the palm to the forehead because we like literally use it every day. And I think everyone, if they see the code, they would recognize that. So let's look at textbook definition. Closure is the combination of function and the lexical environment within which that function was declared. Okay, it's definitely a textbook definition, but we do see lexical environment. We just talked about lexical scope, so there's probably something going on there. And I tried to bring this down into more plain English and say a function still has access to the variables within the scope where it was declared, even if it's called outside of that scope. And I think this one, probably the best way to understand it, you can see that there's a little bit of a difference. Even if it's called outside of that scope, it still has access to those variables. But the best way to understand it is probably through an example. Let's talk about recursion. No, let's go ahead and do an example of that one. It's going to totally screw up my presenter slides, but let's do it anyway. All right. So first of all, let's just look at a really easy example of using the Chrome dev tools to look at the call stack. We're going to be using call stack a lot as we go through this to kind of interrogate what functions are doing. So let's get started here in system one. We're going to go ahead and set a breakpoint here. What this pin is a very simple functional React component. If you're not familiar with React, that's all right. Basically, it's just a function. Button group is the name of the component. It's just a function that takes props and returns some kind of crazy HTML or gibberish. That's all you need to know. So if we look in here, we have a handle click that's assigned to our button, and it's going to call get message. So let's go in here and look at our source. So here we are, we have a breakpoint in get message, and we're going to run this thing. Great. We don't care about scope right now. Let's look at the call stack. Okay, you can see a bunch of crazy function names here. Let's not worry about those at all. Those are just from the React library, and they're just doing everything to get handle click to fire right here. So when we click on that button, it's called handle click, and handle click called get message. So if we look here, I really encourage you to use the call stack in Chrome Dev Tools to kind of see what your code is doing. It's a great tool. But if we kind of click back to the handle click execution context, we can see that it's waiting patiently right here on 45 to return from get message. And oh, you know what? Let's take a look at lexical scope too. We have type up here, defined as some other type. And then in this handle click function, we declared type again as the type property on the props object. And when we see this, sure enough, just as like obviously everyone expected, when we in the console.log call type is equal to warning. So the inner variable declaration took precedence over the parent variable declaration. Let's get back to our call stack example. We're waiting patiently here for get message to return. And so let's take a step forward. it's going to return here warning message. And we'll see here that get message will pop off the call stack. And again, all of these variables that are local variables will be cleaned up when that occurs. So they're no longer useful. So let's do that. And sure enough, here we are back in handle click. And get message popped off the top. Cool. Now let's take a look at a closure. I think that's kind of the more interesting example here. And we happen to have one right here. We have theme background color. So what we're doing here is we have a function that takes a theme, and then instead of returning a value, it returns another function that takes a type. And then within the function that takes a type, it's going to return one of the variables declared in the outer function. So if we put some breakpoints and take a look at the call stack, we'll notice some really interesting things here. I think that should do it. Let's run it. Cool. So we just called get theme background color, and we set a breakpoint there. Now it's creating this execution context, and it's creating these local variables, right? And then it's going to return a function that takes type. But what's going to happen when it returns that? Get theme background color is going to be popped off the stack, and seemingly unfortunate for us, but all of those local variables that we're going to need later are going to be cleaned up because we no longer need them, right? We're out of function, and we're not actually calling this function. We're just returning. So later on, we're probably going to need those variables. So let's just see what happens. Okay, so we're returning, and then let's go ahead and put a breakpoint here just to see what happens. Okay, so now as you can see, get theme background color has been popped off the stack. Those variables have all been cleaned up, but now we're about to call that anonymous function that takes type, and we're going to need to access those variables. So this is where the closure comes in. It seems like it shouldn't work because those are all undefined. We can even take a look here. Yeah, reference area, undefined. But let's take a look what happens when you return that breakpoint. So now calling the anonymous function, we've passed type in, and let's see what we have here. We have a closure that contains all those variables that we needed. So what happens is when this function was returned, when get theme background was originally called, JavaScript saw that we were using variables, and it packaged them up. You think of it like a little backpack, and it stuck with the function and said, like, go on your way. But when you're using, you can open that backpack and still use the variables, even though we're taking them up from the local scope. And sure enough, if we take a look at what's going on with the call stack, we can see our color is defined here, and we'll return. Yeah, so I hope that kind of explains a little bit about closures, or at least gives you a curiosity to keep exploring them. Cool. All right, let's jump back to the slide as quickly as possible. Cool. Next. All right. This one again, kind of like still in our building block segment here. We're going to get to some graph algorithms picture. Slides, recursion is key for those algorithms. Makes them, a lot easier to think about. So what is the textbook definition, method of solving a problem, or the solution depends on solutions to smaller instances of the same problem. Okay, I guess that makes sense. It's like if you call from within itself, right? That's kind of tricky, like some kind of inception thing. Let's take another look at an example. All right. So this is, it's not the most real world example, but I think it'll be good. And when we get to the graph algorithms, we'll take a look at some more complex real world examples here. But what I do want to point out is the usefulness of the call stack once again. Uh-oh. Got code pin frozen up here. All right. Yes, we might have to get to that one later. Are we out of interviews? Bummer. All right, so recursion basically just calling a function within itself. I'll have plenty of other examples with graph algorithms. So let's move on to our first kind of. Oh, went. Hey, nice. All right, so factorial is one way you can use recursion. So one way to do it, a factorial is just taking a number times all of the preceding numbers. So if you see here, like the factorial was 5, it would be 5 times 4 times 3 times 2 times 1. Another way to think about factorials is if you already have factorial 4, answer to that, then factorial 5 is that times 5. So that's kind of the way that you can think about recursion problems. Now this one in particular, you would probably use looping. I just thought it was a nice way of thinking about recursion, and a good way for us to inspect it using call stack once again. I think it's still kind of. Yeah, right. No. All right, but we'll move on to the lead list and kind of the first of the practical examples here. Cool. So a linked list is a linear data structure composed of objects that are called nodes. And each node has a data property as well as a next property. So the data property can be literally anything you want. The next property is just a reference to another node. Typically, the first node will be called head, and the last node next, there is no next, so it'll just refer to a null. And so Adira is tasked with working with the freight team, and they just wanted to create a support flow where the user could report their status in saying in building a package. So they would just have a screen that says like, I'm on my way to the shipper, I'll be late, like this many minutes late, and so on. And so that just created a node. The data was like what we wanted the title to be, and then they could type in, and the next would just go to the next step of the process. Now I hope that a lot of you are here thinking, why didn't you just use an array for this? Because that's a perfect array. You don't need a list to do this. But the answer is coming up on the slide. We knew that it wasn't always going to be a single dimension flow where they can go from one to the next to the next. We wanted to get choices. So we actually moved it into a tree data structure. The support team were paying for enhancements. Why would the driver just report delivery status? There's so many issues that they're manually report. They can cancel those, request payments, reschedule appointments, and so on. And each of those can have many options. Like, I want to reschedule on a different day, earlier or later, and so on. So it turned out it was pretty easy to modify the linked list to just make it a tree so that we could have decisions as we go down. And to do that, we still have the data, but instead of next, there are many next, right? So we call them options because there are options that a driver could pick from. So here you can see now instead of a head, called a root node. And node 1 might say something like, I would like to. And nodes 2, 3, and 4 could say, submit a tracking update, or reschedule my load, or ask about my payments, for instance. Ask about payments, like my payments are late, or when will I receive my payments, for instance. But what we found out with the tree is that, this was a lot better, but we had a lot of duplicates. For instance, like, if you're telling us you want to submit a tracking update, and that you're late, I mean, obviously we should have you reschedule here, and tracking updates here, we were just kind of duplicating whole branches of the tree. So how do you fix that? And the answer is another data structure that's pretty similar to the tree, and that's a graph. So for instance, I said, I'd like to submit a tracking update, I'm going to be late. Or I would like to schedule, I'm going to be late. Both of those should come to you when you're going to be there. What's your new time? So a graph is kind of like a tree, but each node can have multiple parents. So like the 6 has 2 parents. And likewise, parents can have the same node as options. So 2 has 6 as an option, and 4 has 6 as an option. Great. So the project really took off. This is a real project, by the way. This isn't just like some fictional project that I'm talking about. At this point, we have 1,000 tickets coming in every day. And these were things that were previously done over the phone. So they were literally calling into support staff and saying, I would like to submit a tracking update. I'm en route to the shipper. I will be on time. Clearly, things that we could do just through push of a mouse, right? There wasn't a whole lot of back and forth going on. And one major advantage of doing it through an app rather than a phone call is through an app. There's a finite number of paths through this graph, right? If you're on the phone call, someone could say literally anything to you. And so it's really confusing to process those. But through a graph, there's only so many different paths that you can take. So the support team came to me and they said, this is great. We know that there's only these, however many, but there's only a certain amount of paths you can take. In order to train our staff, we would love it if you could give us a printout of every single issue type. We can go through them and just go, what do you say to this? Or what actions do you take for each issue type? So I thought about it. And I've been kind of looking at graphics a little bit, and it became clear what algorithm we would want to use on that. And that is the first reversal. So this is an algorithm where you visit each node of the graph, and you do this by going to the first child of each node as you get there before going to the second child. So let's take a look at what this actually looks like. So we're going to start at root, and then we're going to go to its first child too. And then before we go to 3, we're going to go to 2's first child. This is why it's called depth first. You see how we go all the way deep as possible before going across. 5 goes to 9. Now when we get to 9, we kind of have a special case, right? 9 doesn't have any children. So what we do is we immediately pop back up to 5 and go to 5's second child. 10. Now 10 doesn't have any children, pops back to 5. And 5, both of its children have already been visited. So again, pop back to 2 and go to its second child, 6. Now 6 has one child, 3. We go to that one. And then since we've 3 doesn't have children, so we pop back to 6. All of 6 children, which is just 3, have already visited. So we pop back to 2, pop back to 1, then we go down to 4. And finally, last time we visit a child is 8. So if code panel still works with us, we can kind of take a look, kind of a quick look at the implementation. I don't want to get too into these things. Again, the call is a pretty awesome way to look at recursive algorithms. But we'll walk through this. Can everyone see the code on the screen? Yeah, jump up a little bit. Is this like an internet thing, or?
I'm still seeing the screen share there.
That would be a code thing. Yeah? Yeah. I don't know. Really? Really? Yeah, we don't really have enough to do this without scrolling through it. Let's see if we can open it and see what happens. Cool. Awesome. Okay, so I set up just here, let's bump that up a little bit. I've set up just a small portion of the nodes that are in this actual project. Might be useful to take a look at what the actual site looks like. So I want to be like our root node and then provide a status update when its first child. Interact with shipper, match shipper, whatever. I'll be on time, and then you can submit. So if you think that diagram is just like that, at the root, we choose the very first option. And then before going back and choosing the second option, we would choose that first option, and so on. So we just made it our first list. It's kind of similar to H9. And then at that point, we would drop back and choose the second option. And then again, we pop back twice and choose the second option, this one, and so on. And we can quickly look through the code here. Let's just pay attention to the skip sentences. All right, so here on line 67, we're just going to create an array that's here to handle each of these sentences as they're completed. And then we're going to run a reverse function that's going to look at each return. So the traverse function will begin with that node, and it has a current sentence array that it brings along with it. The current sentence array is going to be each of the sentences. So it'll add nodes to the sentence structure. So I would like to provide a status update, and I'm a shipper, and I will be on time. So if you look down here, we're going to check to see if the node has any options. So we've already pushed the value to the current sentence. We're going to check to see if it has any options. If it doesn't have any options, then the sentence is complete, right? That means we reached 9 and we've gone through the whole sentence. We'll push that to sentences. If not, we're going to go down each of those options, and we're going to do the same thing. We're going to traverse. So for each of the options, run this whole function. And we'll see that when we do that, we end up with every possible route, starting at 1 and going through. Again, I think it's pretty interesting to take a look at the call stack for these things, especially with recursion. So let's just put it right up here, and that'll be fine. Let's run this thing. Got some random breakpoint here. All right, great. Again, let's not worry about all these weird function names that are part of React. Here you can see that we're in all requests. We're in get synthesis, which we're looking at. It's called traverse for the very first time. So at this point, we have just called traversed here on line 68. Line 68. What's going to happen is this is going to get down to for loop. And of course, it has options, so it's going to traverse its first option. And if you look, the option, let's take a look. This is a little bit easier to see. Our current sentence says, I would like to, and then it's pushed the node value of live status update. It's pushing the value, and then it's going to come down and call traverse once again on this node's first option. So we look here, current sentence, I would like to live status update in our shipper. So let's just do this a bunch more times. Now we've reached the end. Interactive shipper and Alves. You can see that traverse, since it's recursive, is being added again and again to the call stack. So the danger with the recursive algorithm is that it'll just call itself indefinitely, right? And what's that called? Yep. I think everyone has been to the site many times, and its namesake comes from not just recursive algorithms, but in particular recursive algorithms that call themselves over and over infinitely. Eventually, the computer or the system just can't handle it. So all recursive algorithms have to have what's called a base case. And in this one, this is our base case. If node.options.length is 0, and again, that occurs when right now we've reached this point. So node.options.length is equal to 0. Put another way, we've interrupt shipper, I'll be on time. And again, this one doesn't have any options, so it's going to pop back up. So what happens is we're going to hit that now, and you're going to see that this top one pops off. So there we go, pop back, and now if you look at the current, current edge value, we're at I'll be on time, and then if you pop back again, we reach the end once again. So we reach on time, we get on late first, and then we reach it on time. And just to kind of make this a little bit quicker, basically we reach here, it was I am late, so we pop back here, and then we reach the end again, I will be on time. So if we kept going, this is a smaller representation, but we can then jump up and move down to here, and all like that. I'll have the code online. I don't think it's useful to really go too far in now. So let's move on to our next one. super speed. Awesome. So for our next algorithm, I could probably come up with some case where we would use, it's going to be breadth first search. I could probably come up with some case where we would use it on the project that I worked on. But I think a much more interesting case of it is the social network case. So in LinkedIn, you'll notice there's this feature where if you're looking at someone's profile, you might say, like, oh, do you know your third-degree connection with this person? Like, you know Frank knows Tom, so maybe Frank can put you in contact with Tom. And so say I'm root node, and we're going to make this just a little bit more complicated so that the value of this algorithm really becomes clear. But say I'm the root node, and I'm looking at Frank's profile, and I want to know, is there any amount of my friends that I can talk to, like care how many, maybe I go 3, 6, and 4, and finally they'll put me back into contact. But I think it's pretty clear from the picture that I would want LinkedIn to tell me, Susan knows Frank. Let's make this happen. So if you look at our depth first traversal, maybe that's the first thing you think of. Like, I already know a way to check if there's any path between two nodes. Why don't we do our depth traversal, and we'll kind of change it just a little bit so that when we find that path that matches, we can just stop and say, here's your path. Let's see what this would look like. So we're going to perform a depth first traversal, but when you reach the desired node, immediately return the path you've taken. We'd start at root, and again go all the way down to depth. 5 goes to 9, 9 has to go back up to 5, and to 10, 11, 12. And LinkedIn says, congratulations. You have friends that know Frank. You talk to Jim, talk to Shirley, Shirley will talk to Bob, to Jim, to George, to Frank. And then Frank will tell George, Pam, and yeah, I can't remember. But obviously this is not what we read, right? So this kind of shows us that multiple algorithms can get you what you want. Maybe it's not the best. So another way to first search is we could try it. And we can do it just like we did before, the depth first traversal. So we can see that this one's this link. Okay, that's one option. Let's try another way. This way. It's another option. And now let's try this way. And let's see which is like the smallest option, which is the least connections. So that's why you can do it. But it turns out there's a much better way than doing that. And that way you can literally check every single iteration to find the one that you want. You need to check all paths and choose the minimum. But luckily, we have breadth first search. So where depth first search goes all the way down before it tries anything else, breadth first search is kind of the opposite. It's going to start with your root, and then it's going to try 2 and 3, 4 on one level. Then it'll go down to 5 and 6, and finally 8. So it may look like this isn't too much better than every path. But in fact, you're only checking each one once. And also, you need to think about the case where this depth could be thousands of people deep, right? You could go all the way down hundreds of people until you finally find a connection. Whereas breadth first search will take a more informed approach to it. And the key to breadth first search is that as you're adding, as you're adding new nodes, what you're going to do is you're going to go here, add all these children to like basically an array. And then you'll check the first item in the array is the item you want. If it's not, you'll add all of its children, but the end of the array. So you're gonna go in the right order in that way. And the key to actually making this work with the breadth first search is you have to know when you get to a node, who added that node in the first place to the queue. So when you're doing this, for each of them that you add to the array, you say added by. So when you get to 4, you're going to add the children 6 and 8, and you're going to say 6 was added by 4 and 8 was added by 4. That way, when you get to the very bottom, you'll find 8, and then you'll say, well, who was 8 added by 4? And 4, who was 4 added by 1? And then you'll have your chain down. We can take a quick look at that code. Cool. You'll see that I've modified the nodes a little bit that we're working with. One, they have a visited property. This is pretty important with graphs because you can, especially doubly linked graphs. So for instance, if you think about LinkedIn or Facebook, you could be my friend, but I'm also your friend, right? So if you start at me and I go to my friend, my connection, and then I'm also his connection. If there's no visited property, he might say, okay, well, the first person I'm going to check is you again. And then I'm going to say, well, the first person I'm going to check is you again. And it could just cause an infinite loop doing that. So you always have visited property on those nodes. So I can, basically it's like tags. Like I'm visiting you, you go through all your connections, but not me. And then they would visit another one and say, don't look back at me again. And then also the added by, and that just becomes important at the end. When you go to track back to your actual path, you need to know who added who. We'll just briefly take a look at the code. We have get path. We have our queue. And when we visit the root node, we're just going to set it visited as true and call traverse on that root node. So again, you have our base case. This is recursive. So we're just going to say node value is target value of the node, and then take that node and track it back using by property and create. If it's not equal to the value you're looking for, then we're going to add each of its connections to this array. And then at the very end of that traverse, we're going to pop the next item off the array and visit that one. And as we saw in our diagram, using the array allows you to do them in order. So it allows you to start with one. You'll be adding 2, 3, and 4 to the array. And then when you call 2, you'll be adding 5 and 6 to the array, to the array. And you'll be using the first item after popping off 2, which will be 3. 3 will add 4 and 6. But it'll add it to the end, and you'll go to the next item in the array. Hopefully that makes sense. If you want to check it out, it's on the code. And I think it's really interesting to kind of observe the different approaches for implementing depth of search versus breadth of search. Cool. That is all I have besides. We're going to get to watch this in the turbo mode too. Cool. So recommendations. So I would really even if my presentation hasn't proven that these algorithms are great on their own, I would just really encourage you to go on a site like Code Signal, LeetCode, and just do like a real like do the breadth of easy problems. It's
really
unfortunate that I got so excited on candidates and then had them come in and not be able to implement, a very reasonable and easy code challenge. And I think it's understandable. Like a lot of times in your daily work, you go about things in your own search pattern every time, and maybe not expose these kinds of things. But not just in interviews. You're going to come across these problems where you need a more complex implementation. These sites will make you more familiar with each of the data types, so that when you do run into that situation that isn't 90% of your workday, you'll know what to use. And then almost just as importantly, it'll get you really comfortable with all of the with the JavaScript as language, with your implementation. And you'll be really surprised. Even if you're an experienced developer, if you haven't been brushing up your skills, I promise you'll be surprised at how difficult it can be. But I also promise you that it'll become easy really quickly, which is great. If you are studying for an interview, plan to be really awesome for your name, but basically like live in where you switch off the interviewer and you with someone else online. Everyone I've met through it has been like super professional and cool. And then on the practical side, I think this is one of the most important things in my development is to look at the implementation of some common utility libraries and see if you can implement them. First of all, just look through the really interesting great one, and then see how you would implement maybe the same thing. This is like basically getting to apprentice under some of the smart engineers in our field. So why wouldn't you? It's a no-brainer. And then I would recommend sites to find the source code. I mean, I guess it should be obvious that's open source, but you can go see all of those built-ins in their open source code. So like, the source for the find method, or the source for the map method, or reduce, or whatever. Unfortunately, since they are an actual JavaScript engine, they'll drop back and use native like C code to do some of their stuff. So it's a little less like to see that. But I would definitely go with Lodash and just check out some of their implementations and try to model your own code after them. That's all I got for you. Any questions?
I also came across a site called exercise.io. Exercise, but not with the E. Yeah. It ends with .io. Where you can practice. So they give you a lot of challenges, like Java, JavaScript, or any language. And then there is a mentor. You submit your code, and they will write comments like, hey, you can do this better way or something like that.
Oh, cool. Fair enough.
Exosystem.io.
All right. Yep.
I would add, my list has some of these things, but also the algorithm design manual, which is the Red Bible.
Nice.
And so that actually has a really great section that talks about just really basic, like data structure, theory, and that sort of thing. It walks you through. This is an array. This is not an associative array. This is a graph.
Nice.
It actually walks through all of those things. It gives concrete examples of why those things would be interesting in certain scenarios. And if you're going to be doing any actual interviewing, I would highly recommend buying yourself a whiteboard and practicing on that whiteboard. It's one thing that I do when I'm interviewing people, especially for senior positions, is I look at how they manage the whiteboard space to communicate effectively with other people. Because there's only 60 minutes in an hour. And if you want to spend like as much time in that design meeting getting stuff done, then really kind of manage space and have good penmanship and being able to present in this sort of scenario, it's really powerful.
Nice.
So those are two tips that
That's a really good point with the book. I'm often like a little bit reluctant by books in the JavaScript land, just because things change so fast. But these concepts are timeless. Like, I'm sure that someone could have given a presentation on debt versus reversal, I don't know, 20, 30 years ago, probably longer, and it would have been exactly the same.
No, I would be surprised to get this kind of question for a JavaScript interview, right?
Yeah, I mean, I think like we're interviewing to be perfectly honest, we don't do quite like a first problem, but we do problems that make you prove that you know the concept of graphs, and we might do one where you walk us through conceptually how to do something like debt first search or debt first traversal. And really, we're not exactly hiring for. I think that it's such a blurred line now, right? Like, I don't consider myself a JavaScript engineer. I use JavaScript for a lot. I saw people looking shocked. I use JavaScript in some of my projects, but we use all kinds of languages. And I think that one of the coolest things about this kind of thing, about these concepts, are that they're really language agnostic, right? Like, you do that in Go, you do that in JavaScript, whatever, it doesn't matter. Maybe you don't do recursion in certain languages, but in general.
Yeah, I don't remember the interview question which involved the recursion. At the first search, or maybe Amazon. Is it? Really?
Recursion is I feel like I would ask a question about recursion. Yeah.
Well, the problem with asking a JavaScript recursion question is the browsers tend to ask so little memory that players ask so fast that less memory intensive way to solve.
Also, I think you talked about practicing on the whiteboard, but there is a disadvantage because nowadays they are using code or pad and all that. That immediately compile. You have to run the code, and you'll be just practicing in the whiteboard. You think that the code will compile, but it's probably wrong.
The point of the whiteboard exercise isn't, are you thinking the point of the whiteboard exercise is to listen to you think through the problem and to ask questions and try to sort of really suss out what's going on there. If you step up to the whiteboard and start writing code immediately based on the requirements that you hear, you're going to erase it 3 or 4 times before you finish the solution. But if you take a step back and you really take the time to communicate with the interviewer, and you really the requirements, and you pick up the edge pieces, then you can lay it to the paper or to the board and start doing real work and writing the code.
Yeah, I always miss that part. Recently, I was asked to design a library management system, and first thing I went was, without any asking any questions about what the interviewer was looking for, I just started writing the classes on whiteboard, which was probably the reason they didn't call me back.
I would also point out, to your point, if you're the type of person that really likes to think things out in head, or kind of like don't make any noise before writing out your solution, you would really benefit from doing it whiteboard or something like Cramp, because like you said, what we're looking for is how you could make a problem, maybe how you break it down, and even how you work with other people. I think a lot of people go to interviews thinking that the interviewer is just going to sit there silently and like stare them down as they do the problem. If someone wants to work with me while I'm interviewing them, I would love to see. I would want nothing more than to see how you work with me. So when someone asks me a question like, how do you feel about this? This is what I would do. How do you feel about this approach? I'm not going to just sit there and be like, I can't tell you that. I'm going to say, I think that's a great approach. That's how I would do it. Or I would say, I like that approach to start out. Let's go with it. And then we'll come back later and clean it up a little bit. Or I'll honestly tell them, I think you're going down the wrong path. Maybe you should think of it a different way. So if you're someone who's really quiet and likes to think a lot, like I think you're going to need to, take a more collaborative approach with solving these problems. Cool.
Thanks, guys.
Thank you.
So you work for Google?
Yeah.
Google is in San Francisco?
No, so I'm one of the few remote people.
Oh,
Yeah.
Let's all thank Tyler again for a great talk. I've been in software engineering in one form or another for 23 years, July. A lot of different languages, a lot of different platforms, a lot of different teams. These days I work primarily with JavaScript. And what I really appreciate about this talk is it gets back to kind of fundamentals. So I'm constantly trying to, as I mentor younger engineers, to get them to be thinking about these kind of fundamentals, not only of the JavaScript language itself, but the data structure and algorithms. While I don't often use trees and graphs, they're tools available to me. I've given pretty much all of those questions, except maybe and others that's corporate JavaScript. But I've got a guy, got my level of experience, Java guy, who was a self-proclaimed expert. And I asked him to find the successor of a random node search tree. Like, I'm not going to do that program. Use trees, job. So, well, not that often. There's occasional. No, day-to-day work is probably use binary search. And I'm not doing it. Like, so wait, let me just, I can write this down. You're using coding. So my guess was like, he was just full of hubris or like it. Hadn't put all those data structure for a while and then forgot how to do it, which is also okay. I don't really care what you solve the problem. But to Tyler, what I'm looking for is how your thought process works. How do you go about approaching the problem? Talk me through it. If you get stuck, that's okay. That's okay. I want to understand that you know the problem space, and more importantly, you can iterate on the solution. So I really appreciate the talk. It was awesome. If any of you want to stand up here, just like Tyler did tonight, as well with your knowledge, let me or Garvin know. Otherwise, we got the room till 8:30, but why don't we clear, take conversations outside so Paul can go home. Thanks everyone for coming, and we'll see you next month.